Um, I feel a little bit out of place here for a couple of reasons. One is I have no background in design. Um, More importantly, I feel old compared to all the speakers and the rest of you here. I feel like two generations older, probably, not even one. Uh, but the real reason I'm here is actually my colleagues, both of whom are younger and are more into design, Rahul, Panikar, and Raghu. Neither of them could be here, so I'm just a replacement or a substitute for them. So just imagine a younger, more handsome version of me or something of that sort, and then you'll be okay. But that said, I realized that Sanjay's beautiful talk. As I was listening to him, I realized, okay, there is probably quite a bit of what we are doing that's apt for the audience in any case. So let me begin first with this video. I don't know if this video is going to play. There. So what you're observing there, as you can tell, is a newborn. Hello? A newborn baby being weighed, and the way they do it, and this is standard practice, and then happens in in clinics and villages all over rural India even today. So where they are actually putting the baby inside a little sack and then holding it, and finally using a spring balance to weigh the baby. And the process is cumbersome. Now talk about user-centric design. This is not really the most comfortable thing. You could see the fear on the faces of the various women, including the mother, about the baby. You don't want to really drop the baby, so you hold the baby till the last minute, and then they do this. But there are also other problems as well. First of all, the spring balances are often not in good working condition. They lose their elasticity over time, and often they are broken, so this doesn't even get done. So it turns out that about 30% of newborns who are underweight are not weighed. So roughly in India, the numbers are like about 5 million newborns every year are born below weight. What does below weight mean? 2.5 kilograms or less is considered to be unhealthy, and below 1.8 kilograms is considered to be critical. You have to take the baby to the ICU or something like that. And yet about 30% of those babies are not actually weighed properly. And of course, people don't want to say that, so they report false data. And very interestingly, if you look at the statistics about baby weights, there's usually a peak around 2.5 kilograms. All of a sudden, any number of babies are at 2.5 kilograms, but you know why, right? It's not really the correct thing. So we were thinking about this, and we thought, this is a significant problem because a baby's birth weight is a strong indicator of a variety of problems, including mortality at birth, as well as various growth-related problems that can last lifetime. So if you can actually catch this fact and do something about it, that can actually improve a lot of lives. So can we come up with a different way of doing this, an easier, a simpler way to do this? And this is, of course, the same video. Now what I'm showing here is about the way we are going about it. On here you see the same ASHA worker is now going to take a small short video using a regular Android phone. Doesn't have to be anything fancy camera or anything like that. And so given that set of images or a short video, usually about 25 to 50 frames in a video, that's enough. That's actually more than enough. Can we from that somehow estimate the size and weights of a baby? Well, my background is computer vision, so is the background of a lot of the people that are working for me. And what we know from computer vision is that given a series of photographs or images of a person or an object, we can actually create a three-dimensional virtual shape of that object or the baby in this case. Now, this is like a typical mesh that you might see get used in a lot of graphics and games and so on. So that's the kind of representation that would be created out of it. So here we are seeing actually the 3D shape being rotated and viewed from different angles compared to the ground truth. This is on synthetic data. We started with synthetically created graphical babies and then rendered them and used them as input. So I'll tell you more about the real one in a minute. But there are a couple of points here that you should immediately be concerned about. I mean, I'm saying that you can take a video and recover the shape of the baby. What's the first thing that sounds really unlikely about this to you?
The mass.
Sorry?
The mass of the baby.
Good point. So from the shape, how do we know the weight? So it's not like magical, like, we look at the shape of the baby. Well, it turns out that newborn babies are of constant density. They are almost the density of water. So once you know the volume of the baby, you know the weight. Now, so this technique of weighing will not work for a grown-up adult because there's bone density varies and things of that sort. For newborn, it turns out to be within the 2% or so accuracy. But there is a second problem, which is that you're not seeing the backside of the baby at all in the picture that we are taking. So how do we infer that? It's quite simple. Actually, it turns out, babies are not like chairs. So if you see the front of the baby, you can actually infer the baby backside. So babies tend to be within a small range of possible shapes of objects. And given that, that's actually what helps us, because we know now we are fitting to a particular space of shapes as opposed to modeling any arbitrary object. But the proof of the pudding is really in the eating. So what we did about this is actually we decided, okay, now this is a good idea. We know we could make this happen using synthetically created data. How do we do with real data? So we did a couple of things. The first thing is that we bought, in order to, so you must have heard about deep learning and machine learning. How many of you have heard about deep learning? Yeah, so this is the modern paradigm of machine learning in artificial intelligence that's become so successful and popular, gets widely used in any number of applications. So that's the technology that we wanted to deploy. But to do that, you actually need to have some ground truth. The machine needs to be taught with ground truth input. In other words, we need to have pictures or videos of babies along with their actual 3D shapes, so that we can now correlate the pictures of babies with the 3D shapes and learn how to map, so that when a new baby comes along, we can infer the shape. Now, of course, 3D shapes of the babies are not easy to come by, so we bought this expensive equipment from a company in Atlanta. You can see one, two, there are about 5 cameras, one here, there is one here, and then sort of 5 cameras. In real time, this equipment constructs the 3D mesh shape of the baby. However, this is like $150,000 plus equipment, so it's not something that we see is field usable, but this provides us the ground truth data. Now, what we realized is that this takes time. So right now we have about 65 or 70 babies collected using this equipment. Not enough actually to do the validation. So we started taking an alternative approach. And the alternative approach really involves taking a lot of videos of the babies and hand annotating the babies. Like we can mark the various joints, just the humans going and annotating on the various frames. And based on that, we can actually map to the 3D shape. So it's a little bit more cumbersome process, but one that's easier to start and use. So now this number is actually more. This was about 2 weeks ago, 1,260 babies, but now we are actually looking at more, 1,500 babies. This, by the way, is being collected at Nilofer Hospital, which is here in Hyderabad. Nilofer has the reputation of being the hospital that delivers the most number of babies anywhere in the world. So great place to collect data. In fact, this is still going on. So we did collect a lot of ground truth data at Nilofer, and then we decided, rather than evaluating the 3D shape, because we don't have the mesh, we can't do that, but we can evaluate how accurate we are with respect to the weight. So we said, okay, let's try to see, given the input video, the ground truth weight of the known babies, can we actually learn and then test it on unknown babies? And we've been getting initially very good results. So this is kind of the way in which the annotation is done, by the way. And but typically to do this, we want to also have like a ruler or a small checkerboard, because that gives us the scale, right? Sort of to give us a calibration. And so today we are getting of the order of about 90% recall. We are focusing on classifying normal babies, low birth weight babies, which is below 2.5, and very low birth weight babies, which is 1.8. And as you can see, we're getting very high recall. Recall means that every time we see a baby of that weight, it's properly classified. Precision is that how much mistakes, how much false alarms it has, and so on. So this says that it is about 14% false alarm. So typically what we find is that we don't have as many examples in these segments, so the algorithm needs improvement. But yet this actually, even with this initial result, this is outperforming the conventional method of doing it. So so we have to test it out more broadly in field conditions. Testing it in the clinic condition is not really a proof, but we are quite optimistic about this. Now, going back to the talk about the design, what it is that made us think about doing this? We're looking at, look, this is a fundamentally important problem, and the current method, which seems logical, which is to have a spring balance, still has got a lot of challenges. As a result, it's not getting used. And of course, you can say, why not give a weighing machine, but carrying a weighing machine to rural villages and households, because a lot of this stuff gets done inside the households, it's not likely to happen. So can we come up with a technology that's simple and easy to use, from which we can do this? Right? Now I'm going to switch to a different problem, which is something where we are just beginning to start doing our work. So I won't say a whole lot about it, but just to kind of review. And this is, do you know what this is a picture of? What this patient is likely to be having? Yeah, so it's one of the biggest killers. In fact, it's the biggest killer of any disease, more than HIV and malaria combined. It kills about 1.5 million people a year in the world, and in India alone about half of that number or more. There are about 4 million plus TB patients in India, and the problem is that finding those patients. There are about 1.5 million or so patients that are known because they go to public doctors, but those who go to private doctors are not known. I mean, they go to the doctors, whether they get proper treatment or not, so a lot of this is guesswork. So one of the big ambitions that the Central TB Division of India has is actually to help understand, to estimate the case load so that we can send screening and case workers door to door to catch them. The second area where there's also treatment, but another area where there's a big problem is actually treatment following. People, when they get TB medication, after a few weeks they begin to feel better, so they stop taking treatment. I don't know how many of you have done this, but I have. When my doctor says take antibiotics for 1 week, after about 3 days I feel better and I stop, because I say, who wants to take this? This is kind of giving me more dryness and things of that sort. So turns out it's a bad thing. The bacteria develop resistance, and after a while you have drug-resistant TB strains. So there are a number of methods for trying to encourage people to adhere, behavior-based design. That's actually going on. They do work to some extent, but clearly they're not working enough. So we are now looking at forecasting or predicting which patient might be likely to adhere versus not adhere treatment. So again, as I said, this is early days, and we just signed an MOU with the Central TB Division, where they said, they'll make us their AI partner to help TB division become AI ready for solving these problems. So let me move on to, these are some of the ways in which we're thinking we will do the work. So basically the way we are looking at it is that can we correlate known infection information with other factors such as transmission, susceptibility, and the strength of health system to kind of predict where you're likely to have more cases to look at. And for the adherence, again, people's other behavioral data, demographic data, and use that to predict who else is likely to behave the same way. Okay, now this is a bowl of cotton. You probably recognize it. Now cotton is an important crop in India. It is the most important aspirational cash crop. Maharashtra, the state we are in, is one of the largest cotton states in India, and perhaps one of the largest in the world. Yet cotton is subject to a variety of problems, and one of the big challenges is disease. Cotton gets attacked by many pests, but there are about 6 that are significantly bad for cotton. And about a year or 2 ago, 50% of cotton got wiped out due to these 2 pests, called American bollworm and pink bollworm alone. And as a result, farmers lost their income. And this happens every alternate year or so, to a point that farmers accumulate debt over time, and you've heard of farmer suicides, I'm sure, becomes a huge social and political issue. Can we help them? Now, here is again something we need to understand how we can help them. So if you look at, to begin with, if you just think about pest control itself, you may think about it one way, but look at what the cascade of cotton farming is. There is already, there's a step of actually doing spraying and preparing the field, seeding and so on, cultivating, and pest management, and then also, doing more soil management, also, harvesting, and then inventory management, and then setting prices, etc. Right? So there is a whole cascade of thing that happen with any crop, because this is not particularly unique to cotton, but certainly specific to cotton. Now, there are a number of places where we could help. We can help here, and in fact there are people who are helping here, reducing the cost of production or increasing the yield. What we chose to do is this in particular, and there was a reason why we chose to do this, is because we saw a care system Okay, so I don't have a picture of it. That where we thought that we could attack. So the way this works today, for example, is that people know this problem obviously exists, so it's not like a problem that has been unattended, even though not successfully. What's the challenge here? The challenge here is actually timely management of pests. In other words, timely detection of pest infestation and applying pesticides in the proper fashion. Of course, you don't want to use a lot overuse pesticides that destroys the soil, creates other problems, health problems, environmental problems. But also it's very expensive. I mean, already the farmer is operating with very small margins, so you want to minimize the use of pesticides. So there is a process currently that exists that is developed by the government called something called economic threshold limit. In other words, until the pest infestation reaches a certain economic threshold limit, you don't use pesticide, and when that limit is reached, you are advised to use pesticide. But who does this economic threshold limit counting, and who does the advising? So the way that's done is in every village there are a couple of plots, there may be one plot or two plots that will have these type of pest traps that are set. These are yellow sticky paper, pests come and stick to them, so you can kind of count how many pests are infected. There is a different kind of trap called the pheromone trap, which looks like a little bag into which they apply some pheromone, so it catches and attracts certain kind of bugs. There are two kinds of traps that are used. I'm not showing a picture of the pheromone trap. What farmers and agriculture extension workers who advise farmers do is to use these as places where they can start doing some measurement of pest infestation. So they empty the pheromone trap on a paper and count the number of pests, and they're supposed to do it on a daily basis over a period of time to understand how the infestation is growing. And it looks like if the infestation is going to be severe, then they can take action. However, two problems. One is that the counting is not easy. This is what it looks like. I mean, how will you tell the bad bug from an unnecessary bug that might be there that may not be a problem for you? And you do need to apply different kind of pesticides depending on which bug you want to kill. So you want to have a good measurement of whether it's a jacid or a whitefly or sucking insect of some sort versus the bollworms which catch in the pheromone, and how many of each of those kinds that you have. Now the way that's done today is that people manually do it by eyeballing it, counting it, or measuring it whatever they want, and that information is entered into an IT system that already is there in place, and this information then goes to a central place where it's kind of integrated across a bunch of villages. So what typically agriculture experts tend to do is to average the number over a block of 100 villages, and then if the number exceeds the threshold, they issue an advisory for all 100 villages. Now already you can see the problem. Averaging, so the number is not accurate. Averaged over a bunch of villages, so it's not a local information. It takes a bunch of time for the agriculture experts to get together and do it. They meet once about 2 weeks or so if they do that. So by the time all of the decision is made, it's almost like 2 or 3 weeks, and sometimes that can be too late. So we saw here potentially a simple, not simple, but a very specific solution we could do, which is AI is good at recognizing objects that are hard to recognize even with our own eye. So can we train machine learning algorithm to count and detect different kinds of pests out of these traps? So basically the idea is the farmer takes a snapshot of this picture, and we do this kind of detection that you're seeing here. So this has actually gone on very well. We started doing the data collection last year in the fall. We started doing it last October, so half the season was over, and then we continued it actually in the Rabi season in Tamil Nadu, where they have irrigated farms. So the farmers, they were helpful in helping us collect data. And the great thing is that we just gave a cell phone to the farmers, asked them to take a picture and upload it somewhere, and within a few months we got like over 10,000 such photographs, and then we had entomologists who would annotate these pictures. So that's going on. Right now we are now field trialing 3 of our bug recognition apps as we speak in Maharashtra, actually, because this is the season when the pest infestation begins. So we are hopeful that we will see some result. Now if we are lucky, really lucky, there won't be any pest infestation, so we won't be able to succeed in our field trials this year, right? But on the other hand, if we do have pest infestation, we'll be hopefully able to evaluate how accurate our algorithm does. Google issued a AI Impact Challenge grant last year. They got 2,600 proposals and selected 20, and we got the one of the awards, which is the highest level of $2 million. Now, our mission is really to not just solve one or two of these problems, to create a series of AI-based innovations to address social sector problems on basic lifestyle domains such as basic living, which is agriculture, basic education, health, infrastructure, sanitation actually is a very important part of it, and financial inclusion. But we want to do it in a way where we don't just sort of isolatedly build these solutions in a lab, but build it in conjunction with social sector organizations and to be able to deploy it. So the way we are thinking about is that AI is just a piece of technology, right? In itself, it can do whatever you want it to do. But only if it's embedded in a product which has, which is designed according to some, user-centric design approach, it begins to actually make sense. But more importantly, even if that product exists, unless it's within a solution system, for example, we know that when we provide this weight of newborns, that will trigger a bunch of actions, and there'll be a certain service component, then it makes sense. Finally, there has to be health systems or agriculture systems approach that will have to do that. So before we do any of this, we ask 7 questions. This is kind of going out of the picture, so I'll actually explain this. So first of all, we ask the question, is this a big problem? But we are not capable of knowing that. So we have to partner with social sector organizations, people who represent our users, and governments in order to decide if the problems are important. Can it be solved by AI? Okay, we could probably figure that out. But by solving that problem, like the pest counting, is that actually going to make a significant enough difference for the overall cascade? So we need to believe that. And then even if that is true, can we get the people that are delivering the solutions to actually accept our approach, like the agriculture extension workers or the domain experts? If they see it as a threat to themselves or their job, they're not going to do that. And then of course, can we do the AI? Can we collect the data, or is the data there already to be used? And more importantly, can we find partner organizations that will work with us to co-create and make a commitment to do the pilots and field trials and so on? And of course, ultimately, is it scalable through various systems efforts? So, really the cycle that we use is first we identify an area and then identify a use case, and then start looking at how we can collect the data and develop a technology proof of concept, build the solution, pilot it, and then we'll do this iteration a number of times before we take it out to scale. And not surprisingly, everything below this line really is in the domain of governments and social sector organizations, NGOs and such. And everything above here is typically falls in the domain of tech organizations, and we kind of see ourselves in the middle. So one thing we realized is, when we think about human-centric design, we think about how we understand the particular usage scenario. But when we are thinking about a system approach, we have to expand the same idea to a whole system. In other words, are there system processes, system methods capable of absorbing and scaling the solution? So it's really, in some sense, to me, a generalization of this concept of human-centered design, which often seems to be about a particular piece of technology or product, but this is about how to apply that same thinking at the system level, if you will. So this is what we are doing, and our founders are Mr. Wadhwani brothers, who have generously given us $3 million a year for 10 years to do this work, and my team, the 2 handsome guys that you were in, that I'm substituting for. So, and then we have right now about a 35 people team of engineers and program managers and so on to do this. Thank you.